Hello everyone, this lesson is on the mole. I'll talk about what the mole is in chemistry and get into some calculations involving the mole. So first of all, a definition, as I have here, the mole is the amount of substance that contains as many elementary entities, which could be atoms or molecules, that you find in, this is the standard, exactly 12 grams of carbon-12. This is what we compare everything else to, is to carbon-12 and 12 grams of it. So remember that there are different versions of carbon or different isotopes. All of them have 6 protons. Carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. But here we're using only the one isotope, carbon-12, exactly 12 grams of carbon-12. So how many individual atoms are there in this case in carbon-12? Well, it's a really big number, and that really, really big number is called Avogadro's number. So Avogadro's number, this number here is written in scientific or exponential notation. If we were to write this all out, let me just go ahead and do this. And this is actually rounded, this number here as well, but let me write it all out. This is Avogadro's number. It is the same as 6.02 times 10 to the 23. So hopefully you prefer to write it in this form here than writing all of these digits. If I did this right, that means that the decimal is here right now, and I have moved it over 23 places. If I did put in, hopefully I did the correct number of zeros. So counting over 23 places, we'll put the decimal right here, and that makes it 6.022 times 10 to the 23. So if you have a mole of anything, this is the number that you have. It doesn't matter what it is, if it is carbon, if it is iron, if it is oxygen, or if it's anything else that we're talking about. So as an analogy, what we quite often do is use the word dozen. How many are we talking about when we have a dozen? Well, a dozen does mean that you have exactly 12. Avogadro's number, a mole, means that you have, well, exactly this number here, give or take a million or so. This is then Avogadro's number. This is how many you have if you have 1 mole of anything. So again, this is based on carbon-12, but now we can translate this to any of the other elements from the periodic table or molecules that we might have. So let's go ahead and do that. So the average mass of 1 mole of all naturally occurring isotopes of an element is what's given to you on the periodic table, and that is the atomic mass or atomic molar mass. So carbon does not show it as being 12.00 or 12. It shows it as 12.01. Units are grams per mole. So if we had a whole bunch of these naturally occurring carbon, this would be the average atomic mass collectively for all of those different isotopes of the carbon. If you take a look at other elements on the periodic table, those numbers, the atomic mass, are the average of all of the naturally occurring versions of that particular atom or element. So if you take a look at sodium, it says that the atomic number is 22.99 grams per mole. What does that mean? Well, if you have 1 mole of sodium, and again, that is 6.022 times 10 to the 23. If you have 6.022 times 10 to the 23 individual sodium atoms, this is how much it's going to weigh, 22.99 grams. Sometimes you see the word molar mass as well. So quite often molar mass, we're not just talking about a specific atom, but now we're talking about a molecule and what is the overall mass, not just of the individual atoms, but overall the molecule itself. So molar mass units, again, are grams per mole. The symbol that we use is a capital M for molar mass. This is on the back of your periodic table. Let me just go to that right now and show you on your data sheet where you can find some of this information. So right below the solubility table that we used before, you have a box there and it says molar mass formula. So in here, it does tell us that lowercase n is the number of moles. Lowercase m is the mass, and it's measured in units of grams. The capital M, though, is the molar mass, and that is grams per mole. I'm not going to keep going back and forth, but we also have this equation here that we're going to use, where the number of moles is equal to the mass of a substance divided by the molar mass for that substance. So for calculating the molar mass, then, we'll take a look at a few examples here. So molar mass of water works out to 18.02 grams per mole. If you do have 18.02 grams, that is 1 mole, and that means that you have this many Avogadro's number molecules of the water. So for each mole of water, though, of course, there's only 1 oxygen for every 2 moles of hydrogen. So let me just talk about the molar mass first of all, and then I'll explain that last point a little bit further. So water is H2O. If we have a number in front, that is the molar ratio. So if we do have 1 mole of water, inside of that 1 mole of water, well, we actually have 2 moles of hydrogen, and we have 1 mole of oxygen. So it doesn't quite seem to add up here, but this is the way that it does work. So in water, the molecule that we have for water, there are 2 moles of hydrogen. There is 1 mole of oxygen, but overall, this is still 1 mole of water that we do have. When we're calculating the molar mass, we need to take that into account. So if we want to figure out the molar mass specifically for this molecule, we have to take the mass of hydrogen, which is 1.01 grams per mole, that you find, of course, directly on the periodic table. Oxygen is 16.00 grams per mole. So again, this is for the hydrogen. This is for the oxygen. But we have twice as many hydrogen as oxygen. So we're actually going to take this number, we're going to multiply it by 2. The oxygen, we only have 1. So now if we do that multiplication, so 2 times 1.01 is 2.02 plus our 16, and that's where we get this 18.02. So that is the molar mass, the capital M, for water. And down here, that's what I explained up with the water molecule, is that in each mole of water, it's made up of 1 mole of oxygen and the 2 moles of the hydrogen. So converting between, moles and moles, going from moles in one molecule to moles in another molecule, or in this case here, just figuring out the number of moles in the components that are making up calcium chloride, when you're given the number of moles in calcium chloride itself. So this is very similar to what I just did with the water. So we have this 0.5 moles, just to rewrite it again, of CaCl2. That is our calcium chloride. So again, where does this come from? Well, it's an ionic compound, Ca2 plus, Cl1 minus. We have to balance the charges. There can be no charge in the compound. So that means we need twice as many of these, or we just do the crisscross. So that's why I have a 2 on the chloride and only a 1 that I don't show here on the calcium. So what does that mean? Well, if I have 0.5 moles of calcium chloride, then I have 0.5 moles of calcium because I only have 1 of them. But for the chloride, I have 2 times 0.5 moles, or of course that's 1 mole. So again, 0.5 moles of calcium chloride. We have 0.5 moles of calcium and 1 mole of the chloride. So that's our kind of mole to mole conversion, where we're starting with the moles in a compound and we're determining the individual moles for each one of the entities that make it up, the calcium and the chloride. So now let's get into some of the calculations here. So this is the equation that you do have on your data sheet. So let me just rewrite this again instead of with the backslash, just with the horizontal line. Maybe that'll make it a little bit clearer. So what do all of these different variables represent? Well, you don't need to memorize it because it is on your data sheet. So the lowercase n is for moles. The lowercase m is for mass, and that is always going to be in units of grams. And capital M, that's the molar mass. So that's the one that we just saw for water. Molar mass. And that is in grams per mole. So if I just do a little bit of a calculation here, so that means that lowercase n moles is equal to, if I put in the units, grams divided by grams per mole. And the way this works is the grams cancel out. And this mole here ends up being in the numerator, so we end up with simply moles. And of course, that's what the lowercase n is the number of moles. So just a reminder, this horizontal line, it's not clear to everyone. This does mean divide, right? So you do actually need to go ahead and do the calculation. You don't just put numbers in. For example, 7.2 grams and a molar mass of 16.00 grams per mole. You do actually go ahead and divide the 7.2 by the 16.00 to get that number. So I showed you the molar mass for water. Let's do a couple of other molar masses here, just so hopefully that is clear. How to calculate it, and hopefully you'll realize how easy it is to calculate the molar mass. So carbon dioxide, so in this case here, the molar mass, we're talking about 1 single mole. So this is per 1 mole. In 1 mole of carbon dioxide, Avogadro's number, 6.022 times 10 to the 23 individual molecules of carbon dioxide. What does it weigh in grams? That's what we're interested in, grams for that 1 mole. So let me just flip over to the periodic table here so we can take a look and just see where all of these numbers are coming from. And rather than me going back and forth, let me do it this way. We're going to be using iron in the next example, iron atomic number 26. This is the atomic number, or sorry, the atomic mass here, 55.85. So I'm going to use that. We're also going to need phosphorus for one of our molar mass calculations. The atomic mass is 30.97. We're going to need carbon, which we already saw was 12.01. And we're going to need oxygen, which is 16.00. All of these are in grams per mole, and it tells you that right up at the top here under the key, atomic molar mass or atomic mass, units grams per mole. So for our carbon dioxide then, again, in 1 mole of carbon dioxide, we have twice as much oxygen as we have carbon dioxide. So we do need to account for the fact that we have twice as much. So in 1 mole of carbon dioxide, I do have 12.01 grams of carbon, 16.00 grams, this is grams per mole, for the oxygen. Okay, so this one here is for the carbon, this one is for the oxygen, but I have twice as much oxygen. So that's why I need to multiply that number by 2. 16 times 2 is 32, plus 12.01 gives us 44 16.01 grams per mole. So if you have carbon dioxide, and if you have exactly 1 mole of carbon dioxide, this is what it weighs, 44.01 grams. This is the most involved one that I'll show you here. The one for, this would be iron 2 phosphate, iron 2 phosphate. So I'm going to do it this way. First of all, for the iron, I'm just going to write down what the atomic mass is. And we saw that that was 55.85 grams per mole. The phosphorus from the periodic table was 30.97 grams per mole. And the oxygen that we just saw is 16.00 grams per mole. So I'm just going to do this a little differently, and maybe I'll grab a different color here as well. So now, how many of these do I have? So that is the atomic mass for iron, but this number 3 right here tells us that we have 3 of them. So we need to multiply this number by 3. In 1 mole of iron 2 phosphate, we have 3 moles of iron. So we need to multiply that atomic mass for iron times the 3. A little bit trickier for our phosphate because we have a number inside the brackets and we have a number outside of the brackets. So for the phosphorus, first of all, inside there is just a 1. Okay, remember you don't need to write that 1. There is 1, but this 2 on the outside does apply to that phosphorus. So we need to go 1 times 2. We actually have 2 phosphorus in our iron 2 phosphate. So that means we need to multiply this number by 2. And for the oxygen, there already are 4 oxygen inside the brackets, but we need to multiply it by the 2 on the outside. So we have 8 in total for the oxygen. So now it's a matter of multiplying these together. 3 times 55, 2 times 30.97, 8 times 16.00, and then we're going to add all of those together. So we're going to add this, and then we're going to add this in. And if you do all of that, plug the numbers into your calculator, what you get is 357.49 grams per mole. If you have 1 mole of iron 2 phosphate, this is how much it weighs. How many individual molecules of iron 2 phosphate do we have? Avogadros number, 6.022 times 10 to the 23. So let's do some calculations using that formula now. So if we have a mass of an iron bar, which is 16.8, what you should get into the habit of doing is writing everything down. So what is our given information? We are told the mass. It's 16.8. So we're going from the word equation that we have, and I'm just kind of simplifying it a little bit. What amount in moles of iron is in the sample? So that's what we're trying to figure out, is how many moles we actually have. So if we take a look at the formula, number of moles is equal to the mass divided by the molar mass. So we don't have the molar mass, but wait a minute, we do, because we just go to the periodic table and we can see that the molar mass for, and I'm just going to put here Fe, molar mass for iron, that is just the atomic mass, and that is the 55.85 grams per mole. So you won't be given this. You'll need to find it from the periodic table or calculate it if it is for a molecule. So now we have our given information. We have what we're trying to find out. We have our equation. Now we're going to plug the numbers in. So our mass that we have is the 16.8. Write down all the units all the time. Write the units over here. Write the units when you're putting those numbers into the equation. And we're going to divide that by 55.85 grams per mole. Grams cancel out. We're left with moles. That's what we do want. And when you plug those numbers in, what you do end up with is 0.3 0.300. We won't talk about significant digits right now, but 0.3 moles is the amount that you would actually have. What about the mass? So up here, we were asked to calculate the moles and we were given the mass. What if we're given the mass, or what if we're given rather the moles, and we're asked to calculate the mass? So this one is flipped around a little bit in terms of the equation that we do have. So we'll talk about rearranging equations, the three variable equation that we have, but let's write down what we have here first of all. So read carefully, what is the mass? That's what you're trying to find. We have this many moles. So our moles, and I'm just going to put again here H2O just so we know what it is. Moles, oh sorry, that's the molar mass. Let's do it this way and we'll come back to that. Moles of H2O is the 7.50 moles. The molar mass we just did, right? We calculated that a couple of slides ago, and that was the 18.02 grams per mole. So your equation on the data sheet is the moles is equal to the mass divided by the molar mass, but we already have the number of moles. We have the molar mass. What we need is to figure out the mass. So what you need to do is you need to get this variable, the lowercase m, the mass, you need to get that on your own. So a number of different ways to go ahead and do this. I'll show you one way right now. So if I have it on the right hand side and I need to get rid of it, if it's in the denominator, if I multiply this by molar mass, then they actually cancel out. But the rule is whatever you do to one side, you need to do to the other. So if I multiply the right hand side by the molar mass, I need to multiply the left-hand side by the molar mass. And then I'm just going to tidy this up. I'm just going to put mass over on the left-hand side because that's what we're solving for. And I'm going to put the molar mass and the number of moles over on the right-hand side, and I've rearranged the equation to solve for what we're looking for. So now I'm going to plug the numbers in. Number of moles that we have is 7.50 moles. And we're going to multiply that by the molar mass, which is the 18.02 grams per mole. So in this case, the moles will cancel out. Moles are in the numerator here, in the denominator, in the molar mass. We're left with grams, and that is what we're looking for, is the mass. So for this one here, our mass is going to end up being, what do I have here? 135 grams. 135, that's a 3. 135 grams is the number of grams that you do have of water if you have 7.5 moles. Let's do a couple more here. So calculate the mass of 0.03 moles of this one here that we saw before as well, the iron 2 phosphate. Let's write down what we have. Mass is what we're trying to figure out. Moles, we have 0.03. Always writing down the units. Molar mass for the iron 2 phosphate, we calculated this before, and that was the 357, so I'm not going to do it again. I'm not going to show you how to do it again anyway, 0.49, and this is grams per mole. Our equation was the number of moles is equal to the mass divided by the molar mass. Let me show you another way to rearrange this equation that I think is the easiest. This number is actually over 1, even though it doesn't show it. It's always over 1. If something is at the bottom on one side and you want to move it to the other side, you just move it to the top. You move it from the denominator to the numerator. So now I have mass on its own. Mass is equal to the number of moles times the molar mass, and that's exactly what we have. 0.03 moles times, if you open up brackets like this, it does mean multiplication, or if I put both of these in brackets, that means you're multiplying them together. 357.49 grams per mole. As we saw before, moles cancel out because here it's in the numerator, here it's in the denominator. We're left with grams. That's what we're looking for. This is why you always put the units in. If you end up with some units that aren't what you're looking for, then you did something wrong, perhaps in rearranging your equation. So this one here, when you plug those ones together, I have the number for you. It works out to 12.7 grams. Again, what does that mean? If we have 0.03 moles of iron 2 phosphate, so this will be a little bit less than 1 full mole, of course, a little bit less than Avogadro's number, and we're actually going to figure out how many molecules there are down below. But if you have this many moles of iron 2 phosphate, then this is how much it is going to weigh. So yeah, let's just go back to Avogadro's number for a minute here. So how many actual individual molecules then are there in 0.03 moles of iron 2 phosphate? So if we had 1 mole, it would be 6.02 times 10 to the 23. But here we only have this many moles. So number of molecules of Fe3 PO42, number of molecules is going to be equal to the number of moles times, I'll just put it as a number, Avogadro's number. So that is 0.03 times 6.022 times 10 to the 23. So this is the number of anything per mole that we do have. So if we have this many per mole and we have this many, I'm going to have to squeeze it in here, moles, our moles are going to cancel out in this calculation. Moles cancel out, and what we're going to be left with is just, well, the number of actual molecules that we do have. This ends up being a really big number as well. So Avogadro's number is a big number. If you had 1 mole, that's how many individual molecules of iron 2 phosphate you would have. But we only have this many moles, so multiplying those two together, it works out to 1.81, and this is rounded, times 10 to the 22 molecules. Again, a really, really big number that we're talking about.